Hello, this is Tim Smith, the Academic Support Coordinator of St. John's River State College, St. Augustine campus. This video, Parametric Equations, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will be discussing the definition of a parametric equation, finding a rectangular equation for a curve, objects in motion, tangent lines, arc length, and surface area of a solid of revolution. Suppose x equals x of t and y equals y of t are two functions of a third variable t called the parameter that are identified on the same interval L. Then the equations x equals x of t and y equals y of t, where t is in L, are called parametric equations, and the graph of the points defined by xy equals x of t, y of t is called a plane curve. Parametric equations can be useful for describing motion along a curve. For example, let's take the parametric equations x of t is equal to 2t plus 1 and y of t is equal to t plus 2 for t values between -2 and 0. These equations may also be written as x equals 2t plus 1 and y equals t plus 2. First, let's create a chart where we can plot the different x and y points at different t values and plot these values on a graph. Starting with the lower limit, at t equals -2, x will be -3 and y will be 0. At t equals -3 over 2, x equals -2 and y equals 1/2. At t equals -1, x equals -1 and y equals 1. At -1/2, x equals 0 and y equals 3 over 2. At t equals 0, x equals 1 and y equals 2. Connecting the points leads to a linear relationship. Assuming t describes time, then the linear graph can be described as movement from the first value to the last. We can also look at this another way by solving the y equation for t, then substituting this into the x equation. We first reconcile the parentheses, combine like terms, solve for y to get y equals x over 2 plus 3 over 2. Note this linear equation also describes the graph, but without the time value. Let's find the rectangular equation for the parametric equations x of t is equal to 2 sine t minus 3 and y of t equals 2 cosine t plus 1 for all t between 0 and 2 pi. For this set of parametric equations, we will start by charting the xy coordinates and graphing the equations within the range of t. At t equals 0, x is -3 and y is 3. At pi over 2, x is -1 and y is 1. At pi, x is -3 and y is -1. At 3 pi over 2, x is -5 and y is 1. Finally, at 2 pi, x is -3 and y is 3. This graph is a circle moving clockwise from -3, 3 and centered on -3, 1. To find the rectangular equation, we take x of t and add the 3 to both sides to get x plus 3 equals 2 sine t. Then in the y of t equation, we subtract 1 to get y minus 1 equals 2 cosine t. Divide by 2 to get sine t is equal to x plus 3 over 2, and cosine t is equal to y minus 1 over 2. From here, we use the Pythagorean identity sine squared x plus cosine squared x equals 1. Replacing the values gives us x plus 3 over 2 quantity squared plus y minus 1 over 2 quantity squared equals 1. Take the squares of the denominators, then multiply both sides by 4 to get x plus 3 quantity squared plus y minus 1 quantity squared equals 4. This equation describes a circle centered on -3, 1 with the radius of 2, but without the parameter, it describes a circle with no motion. Next, let's take the same equation and reverse the trig functions. This set of parametric equations will then be x of t equals 2 cosine t minus 3 and y of t equals 2 sine t plus 1 for t between 0 and 2 pi. For this, we will use the same chart and fill in the second row for our new equations. For t equals 0, x is -1 and y is 1. When t equals pi over 2, x is -3 and y is 3. For t equals pi, x equals -5 and y equals 1. For t equals 3 pi over 2, x equals -3 and y equals -1. Finally, when t equals 2 pi, x equals -1 and y equals 1. Plotting these values gives us the same points on the graph, but this one moves counterclockwise from the point -1, 1. Therefore, parametric equations of the form x of t equals sine t and y of t equals cosine of t will result in clockwise motion. Conversely, parametric equations of the form x of t equals cosine t and y of t equals sine t describe counterclockwise motion. Parametric equations may also be used to describe objects in motion. For example, find the parametric equations for the object that moves along the ellipse x squared over 9 plus y squared over 4 equals 1, where the parameter is time in seconds. Note the graph of the ellipse. The motion starts at 3, 0, is counterclockwise, and requires 3 seconds for one revolution. For this, we need equations where t equals 0, x equals 3, and y equals 0. First, we expand the square to cover both numerator and denominator of our original equation, so it can be related to our trig identity. Based on what we learned from the previous problem, for counterclockwise rotation, we choose cosine of t equals x over 3 and sine of t equals y over 2. To verify our choice, we can express x of t as 3 cosine t and y of t as 2 sine t, then plug in t equal to 0 to verify we have the correct starting point. X of 0 is 3 and y of 0 is 0, which is consistent with the graph. For a revolution that takes 3 seconds, we adjust our equations for a period omega, so x of t equals 3 cosine omega t and y of t equals 2 sine omega t. Since a revolution takes 3 seconds, the period 2 pi over omega equals 3, or omega equals 2 pi over 3. Therefore, the parametric equations will be x of t equals 3 cosine 2 pi over 3 times t, and y of t equals 2 sine 2 pi over 3 times t, for t between 0 and 3. To verify, we can choose a time interval like 3 over 4. If we are correct, the motion should equal 1/4 of the way around the ellipse intersecting at the point 0, 2. X of 3 over 4 is 3 times cosine 2 pi over 3 times 3 over 4, or 3 cosine pi over 2, which is 0. Y of 3 over 4 equals 2 times sine 2 pi over 3 times 3 over 4. Sine pi over 2 equals 1 times 2 equals 2. So x equals 0 and y equals 2 is the correct position. Let C denote a plane curve represented by the parametric equations x equals x of t and y equals y of t, where a is less than or equal to t is less than or equal to b. Suppose each function x of t and y of t is continuous on the closed interval ab and differentiable on the open interval ab. If dx dt and dy dt are continuous and are never simultaneously 0 on AB, then C is called a smooth curve on AB. For a smooth curve C represented by the parametric equations x equals x of t and y equals y of t, where a is less than or equal to t is less than or equal to b, the slope of the tangent line to C at the point xy is given by dy dx equals dy dt over dx dt, provided dx dt is not equal to 0. Find the equation of the tangent line to the curve at the given number. X of t equals 2t squared, y of t equals t at t equals 2. By finding x of 2 and y of 2, we get the xy coordinates of the tangent line to be 8, 2. Since x equals 2t squared, dx dt equals 4t. Since y equals t, dy dt equals 1. Therefore, dy dx equals dy dt over dx dt, which equals 1 over 4t. At t equals 2, the slope of the tangent line will be 1/8. Using the slope equation, y minus y1 equals m times x minus x1, we get y minus 2 equals 1 over 8 times the quantity of x minus 8. This simplifies to y equals 1 over 8 times x plus 1. For a smooth curve C represented by the parametric equations x equals x of t and y equals y of t, for A is less than or equal to t is less than or equal to b, the arc length S of C from t equals a to t equals b is given by the formula. S equals the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Find the arc length of the following curve on the given interval. X of t equals t cubed, y of t equals t squared for t between 0 and 2. We start with the definition of the arc length. Then dx dt equals 3t squared and dy dt equals 2t. This gives us the integral from 0 to 2 of the square root of 3t squared squared plus 2t squared dt. Simplify the expression under the radical to be 9t to the fourth plus 4t squared. T squared may be factored out from the binomial and moved outside the radical as t. Next, we use substitution to solve the integral. Let u equal 9t squared plus 4. Du then equals 18t dt, which makes t dt equal to du over 18. We substitute to get the integral of 1 over 18 times the square root of u du. The range of the integral will also change by using our u substitution. When t equals the lower limit of the integral 0, u is equal to 4. And when t equals 2, we get the upper limit of 40. 1 over 18 may be removed from the integral as a constant. Then we rewrite the square root of u to be u to the 1/2. Taking the integral, we get 1 over 18 times u to the 3 over 3 over 2, evaluated from 4 to 40. 1 over 18 divided by 3 over 2 equals 1 over 27 times the quantity of 40 to the 3 over 2 minus 4 to the 3 over 2. This can be simplified to 1 over 27 times 80 times the square root of 10 minus 8, or approximately 9.073 units rounded to 3 decimals. The surface area S of a solid revolution generated by revolving the smooth curve C, represented by x equals x of t and y equals y of t, for t between a and b, where y of t is greater than or equal to 0, about the x-axis is S is equal to 2 pi times the integral from a to b of y of t times the square root of dx dt squared plus dy dt squared dt. The surface area S of a solid revolution generated by revolving the smooth curve C, represented by x equals x of t and y equals y of t, for t between a and b, where x of t is greater than or equal to 0, about the y-axis is S is equal to 2 pi times the integral from a to b of x of t times the square root of dx dt squared plus dy dt squared dt. Find the surface area of a solid generated by revolving each curve about the x-axis of x of t equals 3t squared and y of t equal to 6t, with t from 0 to 1. We start with the equation for the solid revolution around the x-axis. dx dt equals 6t, dy dt equals 6. We then fill in the values to get 2 pi times the integral from 0 to 1 of 6t times the square root of 6t squared plus 6 squared dt. First, we compute the squares inside the radical. Next, we can factor out a 36 from the binomial. That will be 6 when moved outside the square root times the 6t that is already there to get 36t. This leaves t squared plus 1 under the square root. We then let u equal to t squared plus 1. du will then be 2t dt, making t dt equal to du over 2. When we substitute, we solve 0 and 1 for u, giving us new limits from 1 to 2. The new integral is then 2 pi times the integral from 1 to 2 of 18 the square root of u du. 18 can be moved outside the integral. Then we express the square root of u as u to the 1/2. Taking the integral, we get s is equal to 36 pi times u to the 3 over 2 over 3 over 2, evaluated from 1 to 2. 36 divided by 3 over 2 is 24, times pi, times 2 to the 3 over 2, minus 1 to the 3 over 2. This simplifies to 24 pi times 2 square root of 2 minus 1, or approximately 137.86 square units, rounded to 2 decimal places. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.